good. Hi, everybody. Let's get started here. So the pump set is due tomorrow, and given where we are, so there won't be any homework, no extra credit, nothing to worry about over the break. Yeah, not right now, because we're not there yet. And we're just continuing.
For Squid.
For forever. Yeah. All right. So,
No extra credit.
yeah. Good. So, we've been talking about quantum coherence. We had these interesting phenomena. We talked about like dark states and EIT that have had to do with quantum coherence associated with matter. But we haven't really talked about quantum coherence associated with light. I mean, there's classical coherence. We know about interference of classical waves. We haven't really talked about the quantum coherence associated with the electromagnetic field itself, the quantum part of that. And that is, for many people, what quantum optics is. We've kind of expanded the definition. And so now we're going to shift gears a little bit and talk about that, and talk about the quantum electromagnetic field. Now, why do we need, often when we think about quantum field theory, we think about high energy physics. We think about particle physics at very high energy scales, where we have things like particle creation, annihilation, and standard model, all these issues. We're not talking about that here. We're talking about low energy physics, right? EV and below, not GeV, TeV energies. So why are we even worrying about the quantum nature of the field at these energies? What kinds of phenomena do we even see at these kinds of energy?
Energy is by its nature quantized.
True, but what sort of phenomenology do we notice at our energy scales associated with that? Casimir effect is an example. That's true. So there's some. We'll talk about that at some point. Well, the double slit experiment. I mean, we see that it's true that there isn't always an underlying quantum description of everything, because the degree to which we believe everything is quantum, but it's a lot of scales. It looks definitely we don't have to worry about the quantum nature of the field. Yeah.
Photoelectric effect.
Yeah, the photoelectric. Actually, we don't even need the quantum field for that. We'll get to that very soon. But one thing we have definitely talked about, yeah, of course, there's lots of ways. But one example is spontaneous emission. So, if we have an atom with many states, here's the ground state, here's some excited state, say the first excited state, we know that, well, if this was the description of the energy levels of the system, then these are supposed to be, the energy levels are energy eigenstates of the Hamiltonian that describes the atom. And if I were to start the system in one of the eigenstates, and I ask what's the probability to be in that eigenstate at a later time, if this was the whole story, what would be it would be 1. It would stay in that state forever. But we know that's not what happens. What happens is that over some time, the probability amplitude decays, the probability decays. And so this can't, the physics can't just be described in terms of the interaction of the electrons with each other and the electrons with the nucleus. There's got to be some other physics going on that is causing this phenomenon. And as we said, as we described, and we'll get to in more detail in some weeks, that spontaneous emission, arises even if there's no other electromagnetic fields anywhere in the presence of this atom. There's no stray body radiation, there's no stray light of any kind. This will still happen, the atom will still decay, and spontaneous emission is due to the quantum electromagnetic vacuum. That is a more accurate description of the total Hamiltonian of the system is the Hamiltonian of the atom plus the Hamiltonian of the field plus the atom field Hamiltonian. That's the total interaction, where we've had a description like this when we treated the field classically. We didn't have a Hamiltonian for the field, but we did have an interaction between the atom and the field when there was, say, a laser that was being shined on the atom. But even in the absence of any laser being shined on the atom, there is an interaction, and we want to describe that, okay? So in order to do that, we need to quantize the field. Now, this is a very complicated story. I want to just maybe begin by just talking about the whole notion of what does it mean to talk about quantization generally? What do we mean by quantizing something?
One, make an operator.
Yeah, so what we have, so we have a classical physics description. Which has some degrees of freedom, whatever those degrees of freedom are, and to each degree of freedom, classically, we assign a set of canonical coordinates. We might have a Hamiltonian as a function of those canonical coordinates, and we have Hamilton's equations, which tells us how the canonical momentum and canonical position evolve as a function of time. And to quantize it is to say, well, for whatever the canonical coordinates are now associated with quantum canonical coordinates. So to each one of these guys, we assign a set of canonical position and canonical momentum. And moreover, if these are independent degrees of freedom, then the canonical position, all the canonical positions for all the degrees of freedom and all the canonical momenta for all the degrees of freedom all commute with one another, but the position and momenta of canonical coordinates commute unless they're the same, in which case they don't commute. And these are the canonical commutation relations. So to quantize the system is to first determine what are the canonical coordinates that describe the dynamics of the system, and to each of those then assign a position operator and a momentum operator, and then with these computational systems. And that's how we quantize the system. That's our quantum description, okay? I should mention, of course, that the Hilbert space So I could think about, you know, I could think about the Hilbert space associated with come back to this distinguishable. Come back to that notion later. Degrees of freedom, which I like to call DOFs. We would say is the tensor product of the Hilbert spaces associated with each if I have, say, n degrees of freedom. So classically, the phase space is what we call the Cartesian product of all the different phase spaces. The Hilbert space is the tensor product. And I could think about a wave function that lives on this Hilbert space that represents the joint probability amplitude for all of these guys, or I can think about the momentum space wave function. It's typically in sort of standard quantum mechanics how we describe many body physics, right? We have some many body.
Using the tilde as sort of a pun off of the Fourier transform.
That's what I mean. Yeah, that's how I like to call the momentum space wave function. Each one of these guys is a Hilbert space associated with 1 degree of freedom, and it lives on the Hilbert space, which are the square normalizable functions for one of the coordinates. So that Hilbert space we sometimes call L2R. They're square normalizable functions on the real line. Okay, that's the Hilbert space. Each one of these Hilbert spaces is an infinite dimensional Hilbert space in the way I've written it this way. Okay, so you know, just to get our feet wet a little bit, we can think about some simple mechanical systems and how we write their quantum mechanical descriptions. Suppose I have two coupled oscillators. So I might say, okay, here's two masses on a spring. They're coupled by some other spring between them. And let's just think about their motion along this direction. I can think about them any direction. So there's some motion associated with each of these masses. It has how much it's displaced. That way I'll call that for particle 1, Q1, for mass 2, Q2, and there's an associated mass. And I can write down the Hamiltonian associated with that. And it, you know, when you're solving problems like this, as you probably know, often we can think about generalized coordinates that make solving the problem easier. So in this problem, we know that there are normal modes, right? So for example, if the two masses are oscillating together, there is a mode of oscillation that is completely decoupled from any other motion, which is, I'll call it the symmetric mode, which has a generalized coordinate, which is, say, and I could write it with some units as a sum of that. So this is the symmetric mode. And it has some oscillation frequency associated with it. Or there's another normal mode of this problem, which is the antisymmetric mode, where they're oscillating in opposite directions like that. And if I started like that, it'll stay like that, it'll just oscillate like that. And there's a canonical, there's an antisymmetric coordinate associated with the difference between those. And it has some frequency. And in that's a nice set of coordinates to write, because then the Hamiltonian separates. So in the same way that we think about, you know, the hydrogen atom, we go to center of mass and relative coordinates, because then we can separate that's true in classical mechanics. The two-body problem is that way. These are the normal modes, so I could think about the canonical coordinates in terms of these guys with the canonical. These are generalized coordinates, and it might be more natural to write my Hilbert space as, it is a tensor product of the two Hilbert spaces associated with that, but I could also write it as the tensor product of the Hilbert spaces associated with the symmetric and antisymmetric coordinates, okay? That's another way of decomposing it into 2 degrees of freedom. The 2 degrees of freedoms could be particle 1 and particle 2, or symmetric and antisymmetric. Those are different ways of expressing the degrees of freedom, and often we choose the ones that gives us the simplest description of the dynamics. Okay? You have a question? Someone had a question?
I was just gonna
Yeah.
say, like, it's interesting because you can also write the Hamiltonian optics in terms of the bright and dark state rather than.
Yeah, the general decomposition into, that's a different, that's in the Hilbert space. This is about the degrees of freedom themselves. Okay. Right, and so again, I could write down the Hilbert space for the system, and I can think about, for example, in this case, if I were to think about, and we'll come back to this, what are the energy eigenstates? How, from the quantum problem, for this problem, what would you say the energy eigenstates are of the Hamiltonian for this coupled oscillator? So how would I write an energy, I want to write a ket, which is an energy eigenstate of this coupled oscillator. Yes, Nate?
Based off of the fact that you can't be both, like, symmetric and anti-symmetric, I think the two kets would be symmetric and anti-symmetric.
Right, so I would have the energy eigenstates of there's some number in the symmetric mode and some number in the antisymmetric mode, where these are the energy eigenstates these would have energy eigenvalues n plus a half times h bar omega s, n plus a half h bar omega a. Is that clear? So I had one harmonic oscillator. These are the eigenvectors of the harmonic oscillator. I'm going to remind you of all of this, but I implore you to review the harmonic oscillator as much as you possibly can, the quantum harmonic oscillator, because if you don't have that under your belt, it's going to just be a mess, okay? So please, please, please review we're going to review it here today, but go over that really in depth, because you've got to have that like this if you're going to do this work at all, okay? Yes?
I guess just to be 100% sure that Hamiltonian corresponds to the fact that we have a spring system in the classical.
That's right. So I'm just talking about this system. I want to know, if I were to ask what is the quantum description of the motion of these two masses that are coupled together, I can write down that Hamiltonian harmonic oscillator for particle 1, the harmonic oscillator for particle 2, and the coupling between the two oscillators, which actually, when I write it in terms of the symmetric and antisymmetric modes, factorizes. And these are the energy eigenvectors. This is the joint. These are the set of these guys where the ends go from 0 to infinity in integer units is the basis of the Hilbert space. It's the basis of this for just 2 degrees of freedom. Okay? So that's the quantum mechanical description of the coupled oscillators. Okay, but so that's quantizing the motion of these mechanical oscillators. What we want to do ultimately is quantize the electromagnetic field, But first we have to think about, what does it mean to quantize a field? What the heck is a field? What we mean by a field is a dynamical variable that is a function of space and time. That's what we mean by a field in this context. Okay? So example, we can have a mechanical, let's start with mechanical examples. An example might be, let's suppose I have a rigid rod and I have a pressure wave which tells me how much a little mass element is displaced along this direction x as a function of time. Okay, that would give me a pressure wave. Or I can think about, that's a longitudinal wave. That is, the wave displacement is along the direction of propagation here. I could also think about transverse waves, like, you know, a string, and it has some equilibrium, and the displacement of the string from its equilibrium value at this point in space as a function of x is a function of time. So eta, in this case, these two examples are examples of scalar fields. That is to say, the value of the field at this point in space is just a number. We can have vector fields, like the electric field is a vector field. Okay, but we'll start with scalar fields. And in particular, I'm going to start with a mechanical field, because we can think about the classical mechanics and then find the canonical coordinates and then quantize in the way that we just did. When we think about a field, we really have something which is a function that is continuous as a function of x. This is what's called continuum mechanics, because I'm not thinking about a discrete set of particles, I'm thinking about a continuum, right, which makes it hard to deal with, okay? But, you know, there are lots of books written about this, and people work on, you know, if you work with Professor Monsignor Roy, this is what you're doing, because you're thinking about the Earth and how it compresses, and volcanoes, and pressure, and all that. It's continuum mechanics. It's not a kind of thing that we tend to focus on these days, but you know, there's a lot to learn. But how can I think about the canonical coordinates that describe this field? Well, one way to do it is to first, let's just think about what's the dynamics of this system. And then we'll think about what the coordinates are that describe that dynamics. So if I think about this is a pressure wave, this is a transverse wave. In either case, I have the wave equation. So the wave equation describes the dynamics of the field. And in 1D, that is the partial with respect to x squared of the amplitude of the field minus 1 over the square of the phase velocity times the second time derivative okay, so that's the wave equation. The phase velocity will depend on the continuum mechanics, like the square root of the tension divided by the mass density. You remember that? I don't know if you ever learned that. You guys learn waves anymore? I don't know. But, you know, we forgot it. Anyway, that's mechanics, right? And it's got some. So how can I solve this equation? Well, one way we know to solve this equation is to do separation of variables, okay? So if by separation of variables, I look for solutions of the form some function that's a function of t alone and some function which is a function of position alone. So I make this Ansatz, it's a great word. Assumed form of the solution. And when you plug that in, as you know, what you get, and divide by that, I'm going to get 1 over u of x d squared by dx squared u of x minus 1 over d squared 1 over q of t d squared by dt squared of q of t is equal to 0. Okay, so that's just plugging that in and dividing by eta. Again, you've seen this a million times, I'm sure. And then if this is going to be a solution, then this must be a constant. We have the separation constant. And by convention for ease, I'm going to call the separation constant minus k squared, because it makes the solutions nice. Right? Which tells me that I have two equations. I have d squared by dx squared let me just think about my sign here for a moment. Yeah, right. So I have these two equations, oops, times q.
Forgot a square on
This is as a function of x, and this is as a function of t. So I get these two separate equations. We see that this has the form of a simple harmonic oscillator. Particularly, the q of t is a simple harmonic oscillator where this I'll call omega sub k squared. Okay? So q of t, and I'll label each of these now by the value of the separation constant. So there's, for a given separation constant, there's a given solution. uk is some a cosine omega kt plus b sine omega kt. Okay? It's because this is a simple harmonic oscillator. Okay? Where the values of a and b are determined by the initial conditions in time. What about the spatial part of this? Well, it also looks like a simple harmonic oscillator. And what we would typically take of this depends on the boundary conditions. So the solution to the spatial part of the wave equation depends on the boundary conditions. So for example, if I pin the string between two walls so that, and I make it so it's fixed, and I call this eta equals 0, then I have solutions that look like standing waves because I'm pinned there. So I'm choosing that UK at 0 and UK at L is 0. Okay, so I'm pinning. This is what's called hard wall boundary conditions because those walls are damn hard. So in that case, when I have hard wall boundary conditions, my UK has to be, can't be cosine, it has to be sine. And moreover, so there's some overall amplitude sine kx, where k times L has to be a multiple of pi. Okay? Where n is 1, 2, 3. Okay? And so when I have hard wall boundary conditions, my solution for a given given value of k is whatever this guy of k sine k x, where really it's a discrete. We often are lazy, meaning I am lazy, and don't want to write k sub n and understand that k here is discrete. Yeah, Don.
If Ada's pressure, is it a node at the walls?
Yes, I mean, if I had a longitudinal wave, true, I can't push, and so I'm gonna have standing waves of pressure as well in the longitudinal
I
wave.
mean, like right at the wall, okay.
Right at the wall, and right at each wall, but, you know, it has to approach it in this way. Yes, other questions?
You're saying A is QKT?
No, I'm saying this is eta.
Okay.
So, eta, as a function of position and time for the kth mode, is QKT sine k, where k both is equal to this.
You're taking this A.
And I can have any amplitude I want out front.
Yeah.
Okay? So this is an example for one mode. Okay? Generally, what is true, let me just also say I could have other boundary conditions. I could have periodic boundary conditions. So for example, suppose I had the string, but I attached the head to the tail. And I'm going to choose x to be the distance along the perimeter. Okay? And I can have transverse oscillations relative to that. Since this is periodic, I must have that u of L is equal to u at 0. Okay? So what form of the solution, which is a solution to this equation, can have periodic boundary conditions?
It's a sine.
Sines and cosines, I can have both sine and cosine. The easiest way to deal with this is to say I'm going to have either the kx, where k times L is a multiple of 2 pi. That's the easiest way to deal with it. Because I have just sine and just cosine. I'm not taking into account both. I'd have to have both. But so I'll do it as a complex. So it gets a little more complicated because this amplitude itself is a real number. And if I'm going to choose my modes to be complex, I've got to be careful. But we always do it that way. It's just easier to deal with. So in this case, you know, I would have to think about having both the e to the plus I kx. These normal modes, these modes we said are standing wave modes. Normal modes. And these are traveling wave. Normal modes. Again, what makes this a normal mode is that the mode amplitude is a function of time is oscillating with a single frequency. The frequency here is v times k. Okay? These were examples of the symmetric and antisymmetric oscillations of normal modes of the couple oscillator. these are the normal modes of the field, which I can do, and it's done in the notes, by thinking about the continuum limit of a whole bunch of little coupled oscillators. The string I can think about as a bunch of little harmonic oscillators, each with springs attached to them, and take the continuum limit. So I should really think about this just like this, but in the continuum limit. Okay? So I can think about my field, whether let's just concentrate on the real example for the hard wall bound conditions for the moment. We'll come back to the complex ones in a moment. As more generally of this form. So this is the most general form of the solution. This is a solution. This is a general solution to the wave equation. I can think about this as a Fourier series. Okay? I've expressed the general solution as a Fourier series. Each Fourier component is one of the normal modes, and the Fourier coefficients tell me how each one of those coefficients evolves as a function of time. Okay? So each one of these guys oscillates at frequency omega sub k.
Should there be like a coefficient in front of each term?
The Q is the
The
coefficient.
Q is the coefficient. I can absorb that A, so let's just, let me, here's a problem that we used to give for the prelims. We don't have the prelims anymore, but now you know. Okay, I have a string, and it's a guitar string, and I pull it and I pull it by some amount and make it a triangle. And I want to know, how does this thing oscillate as a function of time? So this is my initial value of the field, okay? At time equals 0, this is how much is displaced, and I want to know what it is at a later time. How would I do it? Yeah, it's me.
You do Fourier transformation to get all the different amplitudes, and then they all evolve at different.
That's right. So let me unfold that a little bit more. What you said is exactly correct. What I do, this is the initial value program. I decompose this into its normal modes. So at time t equals 0, this thing is some superposition of the normal modes. It's some superposition of this, and all the other normal modes. And there's some initial solution. How do I find these coefficients?
Inverse Fourier transform.
You integrate.
I integrate. Why do I integrate? What is that doing? You're absolutely right, Alejandro. What is integration doing? I'm projecting this function onto a direction in function space. These are Fourier components. In this case, they're only the sines. The general, if I didn't have these boundaries, I'd have sines and cosines. So these guys, firstly, I should maybe remind you that these are a complete set of functions on the line between 0 and 1. Yeah.
They're also orthogonal, right?
That's right. I mean, they're also orthogonal the way we've chosen them to be. So they're complete, which is to say any function between x equals 0 and x equals L, which is 0 at the origin at x equals 0 and 0 at x equals L, is a superposition of sine waves with the sine wavelength being constrained this way, right? And these functions are complete, which is to say if I sum these functions for 2 points, I get a delta function between the line. Moreover, as Tristan says, I can they're orthogonal. If I integrate over the line, I get something, well, if I want to integrate two functions together. What I get is something which is 0 unless k equals k prime. If k doesn't equal k prime, I integrate these two sine waves against one another, I get 0. If I integrate one with one another, I get a constant, and we can normalize them. So typically I would normalize them, and this is the normalization. Those are orthonormal functions. Yes?
What was the meaning of the summation to a delta?
This is to say that they are complete. That is, the fact that they're complete is to say that this is an expression of completeness of the function. That's to say they form a basis. This is a way of saying that this forms a basis of all functions on the line, at least between this interval with this. So this is a complete orthonormal basis of functions. And so as Alejandro said, I would find Q0 here by integrating my initial guy against the K1. And that would give me that, I'd integrate from this to this, and that would give me this coefficient. And that gives me the initial decomposition in terms of the normal modes.
How do you know what K to pick?
I have to look at every single one. It's an infinite series. So I have to index it by K, or index it by N, and then I would calculate it, and K here, or N, goes from 1 to infinity, where K sub N is N pi over L. This is a mechanics problem, but, you know, I don't know what you're getting your math methods, but this is how you do it. This is the initial value problem, and you find this initial thing. And then if I want to know what it is at a later time, what is the solution?
Or each piece.
Ta-da! It's the same decomposition, but each one of the amplitudes evolves in time, and they evolve in time harmonically, depending on the initial fission. And you solve the initial value problem, and this thing oscillates. This is the same problem. This mechanics problem is the same problem that you have solved in physics 3, 2, 1, I don't know, where you do a particle in a box in quantum mechanics. And you say, here's the initial wave function. And I want to know, how does the wave function evolve in time? 1 second. What I do is I decompose it into all of the energy eigenvectors, which are the normal modes of the Schrödinger equation. And then you know whatever the probability amplitude is evolves in time according to the with that phase. Yes, Tristan.
Is it like fair to look at our solution here that looks exactly like how we solve like every quantum mechanics problem and say it comes from the fact that the wave equation is a Hermitian operator acting on...
Yeah, I mean, it's the same, it's exactly the same mathematics. Whether the mathematics is describing the mechanical wave or the wave function, it's the same exact mathematics. The only difference is with the Schrödinger equation is that it's a first time derivative, but we still do the same thing, and then that's why we have always complex amplitudes. But that's a longer conversation. Okay, cool. And more generally, I can think about the complex cases where I have these as my normal modes with the periodic boundary condition. I just have to be a little bit more careful about that. Okay, so what we have learned by doing this is that the field with boundary conditions is described by a countable number of canonical coordinates. The canonical coordinates are the amplitudes of the normal modes, and there's an associated canonical momentum. So that's an important takeaway here. Each normal mode is a dynamical degree of freedom. And I could describe the mechanics of this field as the dynamics of the amplitudes of the normal modes. And there is a phase space that describes the trajectory of this, which describes how the normal modes are evolving in time. And if the normal modes are set by the boundary conditions, they're like the eigenfunctions of the system, and once I know them, the dynamics are just how do the amplitudes change as a function of time. The end. All right, you ready to quantize the field? See you later. That's it, really, that's kind of the whole story. I'm not kidding. That's essentially it. I'm now just saying that what was a classical canonical coordinate is now a quantum canonical coordinate.
With those commutation relations?
With those commutation relations. Exactly those commutation relations. So that the QK with PK prime is I H bar delta K prime, and every other coordinate. And we now have a notion of the quantum field. The degrees of freedom, again, it's very abstract. Well, in this case, it's not so abstract because this was really, it was a mechanics problem. I come back over here. This coordinate is the coordinate that describes how much of this anisymmetric mode exists. This is like the sign with the one node. This is like the sign with no nodes. How much of this normal mode and that normal mode, what the amplitude is, are the coordinates that describe the dynamics of this coupled oscillator. The dynamics of this continuum oscillator, its coordinates are this. Okay? It is abstract, but not horribly abstract if you think about mechanics and the mechanics of normal modes and coupled oscillators. Okay? So each normal mode is a dynamical degree of freedom, and in this case, when we had just the wave equation, so I have no other interactions other than the natural interactions of the, whether it was the pressure wave or the string with its tension and all of that. For no other interactions, each normal mode evolves as a simple harmonic oscillator with frequency omega of that mode. Okay? So the quantum description of this is the quantum description of a collection of quantum harmonic oscillators. Each normal mode is a harmonic oscillator, and we know what the quantum mechanics of that is, or if not, we're going to review it. Well, we're going to review it right now. So let's, before we talk about the quantum simple harmonic oscillator, let's review the classical simple harmonic oscillator.
What is that?
Forgot.
So let me remind you, okay? Okay, so let me say just classically, what is the Hamiltonian? Well, the Hamiltonian is kinetic energy P squared over 2m, and the potential energy, which is m omega squared q squared, okay? Where the oscillating frequency is square root of the Hooke's constant over the mass, right? If I wanted to, I could write down just very straightforwardly what the Hamilton's equations of motion says, that q dot, which is the velocity, is p over m, and p dot, which is the force, is minus dh dq. These are Hamilton's equations, which gives me Hooke's law. Right? Which I can solve. Now, the first thing one really should do when one wants to look at the solutions to any physics problem is to get rid of the units. You should first figure out what are the characteristic scales in the problem and make everything dimensionless relative to the physical scales in the problem. You should always do that. Every physicist should first understand what is a characteristic length, time, energy in the problem. What does the problem tell us? Otherwise, you don't have any sense of the problem at all. So we're given a couple of constants. The only constants here are the mass and the frequency. But we want to think about how we should relate the characteristic scales. Okay, so there is some length scale, a characteristic length scale, Q sub t. There's some characteristic momentum scale. There's some characteristic energy scale in the problem. Or at least, if I have, they're related to one another in some natural way, okay? So I'm going to define x, capital X, as a dimensionless position. The canonical coordinate divided by the characteristic length. I'm going to call capital P the momentum divided by that, okay? And since that's already capital H, I'll put it, we can make it look like that, which is H with bars on it, which will be H divided by that, okay? So let's write capital H like that, is H divided by BC is equal to, if I write that, that will give me 1/2 PC squared, capital P squared, divided by M BC, plus 1/2 M omega squared QC squared, capital X squared, divided by BC. Okay, so all I did here is I just said Q was equal to characteristic scale times dimensionless. Everyone follow that algebra?
Wait, QC stands.
Sorry?
So
This is a length, this is a momentum, this is an energy.
we don't know what they are.
We're going to determine what we should choose them to be.
Oh, okay.
What should we choose them to be? What I should choose is to get rid of the units, let's call this one and that one. That's how I should choose them. That's an actual. Now, I could choose to absorb the 2 in there if I wanted to. That's up to me. I'm not going to because I don't want to have any 2's or anything around, although it's going to screw us in the end because that 2's going to come back to annoy us. It always annoys
Did
me.
you mean to include the p squared in that one?
I did?
The big p squared?
No, I didn't.
No.
I certainly did not. Thank you. Okay, so I'm going to call this one and this one. Okay, so that means that I only have two constants, so I can't determine everything. The Hamiltonian is whatever the characteristic energy scale is, x squared plus p squared over 2. Where the characteristic momentum scale is the square root of m times whatever the characteristic energy scale is, and the characteristic length scale is equal to the square root of EC divided by m omega squared. So that QC times PC is equal to E over omega. Okay, so I've gotten rid of whatever we only have two constants, mass and frequency. So we can't determine all three constants, but we can relate them to one another. Okay, we can say that whatever the scale we want to choose for energy, they have to be connected if I'm going to make it nice and simple this way. This is the first thing you should always do for every problem in physics. All right, so let's now rewrite our equations, our Hamilton's equations, the equations of motion for Q and P in terms of the dimensionless variables. If I plug in these values over here, what I get is that x dot is equal to omega p, and this equation becomes p dot is equal to minus omega x. Okay? Once I've gotten rid of the units. Okay, so now p and x are dimensionless variables. Omega is a frequency, so this has the right units. Okay? And how do I solve this equation? Well, one way to do it is take the second derivative. It says x double dot is right? Same thing for p. When I go through all that, if I did it the other way, I would get the same thing for p. Okay? And the solution to this equation is x of t is whatever x at 0 is cosine omega t plus whatever x dotted at 0 over omega sine omega t, because this differential equation is determined by the initial position and the initial velocity. That's the solution to that equation, right? Everyone agree? You can plug it in to clear that it has x dot at 0 is this, and x at 0 is that. And it satisfies the equation. So that's the right initial position. Okay, that's the solution. And x dot over at 0, so x dot over omega is p. So this is p at time t equals 0. Okay? So this is one thing I want you to notice, that the position as a function of time depends on the initial position and initial momentum. These two things are known as the quadratures of the motion of the oscillator. They're called the quadratures because they tell me how much of the oscillator is oscillating like cosine and how much is oscillating in quadrature, meaning 90 degrees out of phase. So the x and p are called the quadratures.
The IFEQ that you just solved were from the definitions of x and p, that they didn't involve the Hamiltonian?
Well, they came from the Hamiltonian, because the Hamiltonian told me what the differential equations were. At the top,
Oh,
I use, without the Hamiltonian, I don't get those differential equations. Those differential equations follow from the Hamiltonian. Those equations up there are known as Hamilton's equations. Yeah.
Will the initial conditions affect the characteristic scales at all?
No.
Okay.
The characteristic scales are determined by the differential equations or equivalently by the Hamiltonian or the Lagrangian.
Makes sense. I'm not
Yeah.
just like seeing how we'll get like the length scale, I guess, but that, yeah, makes sense.
Well, we really can't because we don't fully have, but we will in a moment. Hold that thought for a little bit. Okay, so I should say that I can always also write this as some amplitude times cosine minus phi, where phi is a phase, or equivalently a cos phi cos omega t plus a sine phi sine omega t, where this is the initial x and this is the initial p. So that's another way of parameterizing the solution, as you all well know. And from this it follows that the amplitude is the square root of x0 squared, p0 squared, and the tangent of phi, if I look at the, is the p of cosine is x of 0 over p of 0. Right? So if I think about the phase space trajectory of this thing, oh, and by the way, if I look at the Hamiltonian of the system, and I look at it, we said it was E0 x of t squared, p of t squared over 2. That's what we said was the Hamiltonian. If I plug in this, what I get is that this, which is E0 a squared over 2. So the Hamiltonian of the system depends only on what the initial amplitude of this oscillator is. So if I look at this, there's an initial x naught, and there's an initial p naught. And this is the point in phase space, right? A is the length of this vector. Phi is that phase. Okay, that's what this is. The energy of the system is conserved. The energy is just proportional to the square of the amplitude. So what does the trajectory in phase space look like given all of that? It's on a circle, firstly, right? And the next question is, does it rotate clockwise or counterclockwise?
Depends on if you're in phase or not.
No, I start somewhere. The question is, does it go like this? We know it goes on a circle of that radius. That's supposed to be a circle.
Okay. Didn't you just give us the answer?
No. Or I might have. I don't, not saying. But we can look at it from this, right? Which I can write as a cosine phi minus omega t. So that means that I'm subtracting omega t, it goes clockwise.
So that's.
And we can kind of see that, right? If I start the system with, I pull it, I have some initial x and p is 0, it goes back towards the origin. X decreases and p gets negative, right? So it goes around this way, okay? In fact, the solution is equal to the real part of x plus of 0, oh, let me write it this way.
P is positive. X plus 2 plus 1. Oh,
Does everyone see that? If I take the real part of that, I get x0 cos, right? And this thing is a e to the I 5, right? This is the complex amplitude. The complex amplitude encodes the initial amplitude and phase of the oscillator, and it oscillates like e to the minus I omega t. The reason it's e to the minus I omega t is that it's going clockwise, and because we always measure phase this way, that's why in physics is, no e to the plus j omega t for electrical engineering. It's e to the minus I omega t because that's the physical direction in which it's going, right? So,
Flip off the camera.
I was basically,
Yeah,
vaguely. Okay, so, and this tells me that I can think about this as the real part of a e to the I minus omega t. That's what that is. And the real part of that is what we just said, is that. Okay? This is the harmonic oscillator, how you should think about it. Okay, now, there's a little bit of an issue here with the Stam factor of 2. And what we want to do it. So we always, to get rid of the 2, we define alpha is defined as x plus ip over root 2. Okay? With that square root of 2 there. So that what I can then say the magnitude of alpha squared is x squared plus p squared over 2. So that the Hamiltonian is the characteristic energy times the magnitude of the complex amplitude squared. Or I could write it as like that. Okay? And from this, we can see that alpha of t when you plug all of that in, is that, right? Which is equal to the magnitude of alpha naught e to the I phi minus omega. And so phase space is actually also complex phasor space. We can think about this vector in phase space as what's sometimes called a phasor. That's what is often in electrical engineering called the oscillator. And I can, so instead of x, I can call this the real part of alpha, and the imaginary part of alpha with these very unfortunate factors of square root of 2 that we got to drag around because those factor of 2's got to go somewhere. Okay, and so we sometimes call this the complex alpha plane rather than phase space. Okay, very good. So now, with that said, we can talk about the quantum simple harmonic oscillator. And I'll just say a few words quickly, and everyone's going to review this over fall break because what else are you going to do? So now I quantize but in quantum I have a new characteristic scale. What else do I have in quantum mechanics? H bar.
Yeah.
What is H bar? H bar, what are the units of H bar? The units of H bar are, no!
Unitless.
We're going to make things unitless, but they are dimensions of action. And so what should I choose my characteristic length scale and momentum scale to be relative to H bar? How is H bar related to length and momentum?
H bar divided by our x naught p naught? Or characteristic length and momentum?
So Q times P is angular momentum, or H bar, the units of action, right? So now I'm done. Now I have my characteristic scales. Now I have them all. So now we can just say, this says that the characteristic length scale is equal to, so this, of course, according to what we just said, is EC over omega, right? Because that was the natural thing to do to make everything one, was to make this. So this tells me that the characteristic energy scale is what? H bar omega. That naturally falls out. And the characteristic, thus, length scale is the square root of H bar over m omega. And this characteristic length of momentum scale, according to this, is equal to H bar m omega. Multiply them together, get that. Okay? And so to quantize, we had QP is I H bar. That means the dimensionless position times the dimensions momentum is equal to I H bar divided by the characteristic scale, which is I. Therefore, H bar is 1. We've done that. Okay. Okay. So now let's come back here and ask, what is the quantum version of the complex amplitude?
X hat plus
Alpha goes to x hat plus I p hat over root 2. Okay? That operator is non-Hermitian, but we call it A instead of alpha. And a dagger is that. And the commutation relation between A and A dagger using this is that. And you plug all of that in. And so the quantized version of the complex amplitude and its complex conjugate are what we call the raising and lowering operators. But they really should be understood as the quantum version of the complex amplitudes. from a phaser. They're the quantum phasers. Okay? And I remind you thus, finally, what is the Hamiltonian? So the quantum Hamiltonian was the characteristic scale x hat squared plus p hat squared over 2. Right? This is h bar omega. If I plug in here, x is equal to a plus a dagger over root 2. It's the Hermitian part. And p is a minus a dagger over I root 2. It's the anti-Hermitian part with these horrible factors of square root of 2. I think I did it right. This minus this dagger is 2i. It's root 2i. This is correct.
Maybe you did that one wrong.
No, it's right.
Okay.
I'm totally right.
Okay,
I'm often wrong, but this time I'm totally right.
We are giving Deutsch.
We'll see.
He's great at this, man.
Yeah.
I think he's right.
I don't know what Brandon's teaching me, but I'm sorry, Brandon. I'm absolutely 100% right. I'm not this guy. Anyway, then I plug that in. I get that the Hamiltonian is equal to h bar omega a dagger a plus a dagger over 2. Notice, interesting that it comes out this way. Classically, we had that the Hamiltonian was the characteristic energy scale alpha star times alpha. Didn't matter what order I wrote it in because alpha star and alpha commute. I can write those complex numbers in any order. But quantum mechanically, who goes first? A dagger or A? We can't say. But it comes out naturally in this symmetric order. Using this commutation relation, what we have is that this is equal to h bar omega a dagger a plus a half.
Isn't that the number operator?
Yeah, it's a number operator.
And this is the number operator, which has eigenvectors that have integer eigenvalues. The energy is n plus a half h bar omega. All right, we will remind ourselves of this more next time and put this all together to think about the nature of the quantum field. In particular, we'll come back to the one we just solved, this problem, the problem of the strings, where we have this quantum field over here. What are we talking about in terms of these number states? What do they represent in terms of the nature of the quantum field? What is it, and in what sense is the quantum field now a many-body problem? To what, in some sense, quantum field theory and many-body physics are intimately connected to one another. The quanta of the oscillators are going to be quanta of excitations of the field. Those quanta of excitations of the field are what we call particles. That's what a particle is. An elementary particle is a quantum of excitation of the field. In the context of the vibrations of a string or a pressure wave, those quanta are called phonons. The phonons are the quanta of excitations of vibrations of a material thing. The quanta of excitation of the electromagnetic field are called photons. And we'll get to those after. All right, we'll stop there. Yes.